Well, welcome everyone. My name is Mikhail Golovnya. I'm a senior scientist at Salford Systems. And today I will be talking about CART. CART is one of the leading flagship products of Salford Systems. And right now it is sort of at the stage of being fully developed. Now, CART itself was originally introduced by Breiman, Friedman, Olshan, and Stone. And it is worth a little bit of a discussion to trace back its roots and to have a little bit of a historical background. Now, Breiman, Friedman, Olshan, and Stone, as unique personalities, are presented in front of you as their photographs. And it turns out they did not arrive at CART simultaneously. They actually worked in pairs. First, there was Friedman and Olshan working at Stanford, and Friedman wrote a paper in 1977 outlining his approach to decision trees. I mean, back then it was a relatively new and hot topic. Now, Friedman performed some work at Slack, and back in 1974 he was a leader of the computational group. Now, during his work at Slack, he also had a series of helpful discussions with Richard Olshan on the difficult theoretical as well as practical aspects of decision trees. Now, if you're more interested in the results of that fruitful work, I mean, you're welcome to try Google Scholar or some other sources out there. Now, quite independently, Breiman and Stone were working at UCLA. Now, Breiman himself was had a pretty charismatic personality, and he was a professor of mathematics at UCLA in 1960s, and he's also the author of a classic gradual text on probability theory that to this day, that book is oftentimes referred to as one of the best books on the subject. And he also recruited Charles Stone to join the department with a focus on theory. Now, at some point later, Breiman kind of lost interest in theoretical statistics and decided to go on and develop some really important and useful practical applications. So he left academia to explore real-world consulting, and while he was working in the Technology Services Corporation, TSC, he began working on a tree-structured approach to classification. He authored a technical report together with Charles Stone on an early variant of CART in 1977. And then there was that useful stroke of luck when all four met each other at the Interface Conference in 1977, and that event essentially brought all four big guys together into one contact. So immediately in 1978, 1 year after they've discovered that they were working on the same basically same area of research, they pulled out a draft that would outline a CART monograph that was yet to be released several years after. Now, initially, as they were working on the computations and theory, they've encountered some kind of resistance from the conventional statistical circles. Now, if you're interested in the topic, we have some recordings of Leah Breiman's personal recollections on some of the events that were shaping back then. And it's quite interesting. The technology that they were offering and that they were trying to develop was so drastically different from everything else available or known in existence that it would practically scare away a large number of conventionally thinking people. In fact, they were not able to publish the results of the original research in the conventional channels. And instead of doing that kind of fighting with the conventional means of distribution, they've decided to organize everything as a book. And the book itself was first published in 1984, and it is the book that essentially marks the beginning of the legend. So they announced a remarkable new classification tool which could do all of those things. Well, the most important pieces would be separation of important variables from irrelevant. The technique would be capable of learning the actual shape of the underlying response surface without relying on any specific initial assumptions. And a great deal of the methodology itself was also dedicated to the nasty areas in data mining that have to deal with outliers and especially missing values. We once asked Jerry Friedman what is the percentage of CART that actually deals with missing values, and his reply was 80 to 90%. And it turns out they have not arrived at the final version of the code itself as a kind of right away. They actually had to experiment and spent years of their lives in research to work out different approaches, different methods, to evaluate different alternatives in order to arrive at the final version that would be satisfactory on all accounts. So the missing value handling is one of the biggest issues there, even though for an unprepared mind, it might sound like not a very big deal. Now, the interesting part about it is that it could also yield relatively simple and easy to comprehend models, as you will see in a moment once I introduce one sample example of a CART tree. And naturally, as anything in data mining, it would require little to no supervision by the analyst, well, at least in order to build the first-round models. And the striking thing is that, as it turned out, after all that effort and thought that was put into the development of the product, the end result is that nowadays a very first model that you would normally get with CART is usually pretty good, or at least it immediately points out on some problematic areas in your data set or even your own mistakes. So the approach is described in the book titled Classification and Regression Trees. The original day of publishing is 1984, and it's also became known as the CART Monograph. If you need to find one authoritative source of information on the details of the technology, then the CART Monograph will be the right direction to go. Nowadays, you may also find other books. There are smaller and larger books that somehow mention CART. CART has become more or less established technology out there. But to this day, the ultimate answers to all possible questions can be found only in the CART Monograph. The initial years of CART, after the book has been published, and together with the book, there was actually produced the self-contained piece of Fortran code. The initial years were marked by some kind of struggle. There were naturally multiple reasons for that. The monograph itself is not an easy read. It definitely requires at least a gradual level of understanding of statistics, even though some initial chapters written by Breiman himself are kind of a gentle ad hoc introduction into the beauty and usefulness of classification and regression trees. The method was new. It was not expounded in any way in the available textbooks. And as the result, it was taught only at the advanced graduate statistics classes at a handful of leading universities, well, at least back then. And the code itself was in Fortran 77, which was back then a big deal, but in order to run a code like that, you would have to be both a programmer and a statistician, which is a combination to this day, which is kind of hard to find. And the method itself was naturally radically different from everything else that was available in existence back then, and it really did require some kind of restructuring of your mind and attitude in terms of how to deal with data. What do we mean by modeling? What do we mean by pattern discovery? And so on and so forth. Nonetheless, some of the leading researchers discovered CART back then, especially in the fields of medical science, as well as all the people that were in any way affiliated with various consulting projects that the Big Four were back then involved with. So that all eventually led to the final triumph that could be dated back to mid-90s and later. And the big part in that overall development played also the existence of Salford Systems, which is the company that decided to take the original CART source code and, according to the agreement, exclusive agreement between us and the creators of CART, to place the product into a commercially available form. And at some point, there became clear advantages of the use of CART. So for example, there's all sorts of advantages of CART over other three methods. That includes handling of missing values that I have already mentioned. You may also find it a very useful and alternative way to explain what is happening in your data set, or what are the driving factors that control all of the key players. You may also see some of the performance advantages in terms of speed, accuracy, and ability to handle large data sets. So we, as Salford Systems, sort of carry the torch of CART. We're making it available to the large masses of people out there, and to relieve all of that initial difficulty of trying to compile and use the kind of Fortran 77 original code base. In the modern day CART, you no longer need to worry about those strictly programmers' domains. You basically take the software, you run it on your data set, you look at the results, look at the performance, and become extremely efficient in delivering the high-level accuracy models. So what is CART? Well, it stands for Classification and Regression Tree, and it is best illustrated with the famous example, the UCSD heart disease study. Now, that example has some historical interest because it just happens that the creators of CART were initially involved with the UCSD heart studies, and they were actively using new technology and that new machinery in order to help advance the health science. And it's also important that basically, based on the results of those studies, it is the medical community that was initially most responsive to the advances of CART. Doctors were not puzzled by seeing decision trees. Unlike statisticians or people who would normally think in terms of p-values or hypothesis testing or linear equations, seeing a decision tree would essentially reproduce what would happen inside of the doctor's head when he or she is making certain diagnostic decisions. So let's look at this study at a somewhat greater length. Suppose we have an emergency room, and the emergency room is receiving patients with the symptoms of the heart attack. There's some kind of chest pain, there is all kinds of bad feelings, etc. Now, we want to predict who is at the high risk of a second heart attack, and this is the result in early death within the next 30 days following that initial admission. Now, naturally, that prediction is needed in order to determine the treatment program, the subsequent follow-up programs, the insurance costs, the kind of whether we need to have some intensive therapy or things will kind of stay on their own, and so on and so forth. Now, for each patient, they've collected about 100 variables initially. But then that list was subsequently reduced down to 19 non-invasive variables, or the variables that are either easily obtainable or self-evident. Things like age, blood pressure, gender, some rudimentary medical history, but certainly not variables that would involve some fancy test labs or exploratory surgeries or anything like that. So those were all eliminated. They've also eliminated variables that had high percentage of missing values or would require some specific knowledge not always available to the rank and file patients. So in any case, we have a very straightforward classification task here, screening out the patients that have a high risk of dying within the next 30-day period after the initial admission, using only the variables that are either easily obtainable or directly observed. Once you take a data set like that, and they took actually a set of 215 patients observed in the past at the specific locations, the specific emergency rooms. So, and they also observed who of those patients actually did suffer the second heart attack and who did not do that. So, and they nominally called the first group as the dead group because they actually were concerned with those who did suffer the second heart attack and died as the result, versus the surviving group who either did not suffer that second heart attack or basically survived without much trouble. So they took that data set, 215 patients and 37 dead and 178 survivors, and they used CART in order to screen out all of the input 19 variables and in order to build a model that would communicate the actual picture of the risks associated with the heart attack. Now what you see in front of you is an example of a classification tree, and the tree itself kind of grows from top to bottom. In the root node you have the entire data set with 215 patients, 17% of which is namely 37 patients, did not survive, and 178 survivors. What CART is doing with this data set, it's searching for the best way to separate one group of patients from the other. And what it found here is that if you take blood pressure, well, obviously systolic, and if the blood pressure below 91, then you have a small group marked as terminal node A with only 20 patients, 70% of which did not survive. The rest of the majority of patients goes on the right-hand side, and this group is further partitioned based on the age descriptor. All of those who are younger than 62 and a half go on the left-hand side, and they are all gathered together into a terminal node B with a very small death rate. Everyone else goes on the right-hand side, and then these are older people with high systolic blood pressure. And for that group, the next question is whether they had irregularity of a heartbeat condition or something like that. Now, those who had it are separated on the left, and they have an increased risk of dying, and those who aren't separated on the right-hand side, and there the risk of dying goes down to 11%. And that's pretty much the end of the story. Now, in our CART training classes, we usually spend much more time on understanding this example as well as kind of discussing some important features that make CART different from the competing decision tree technologies available out there. Now I will skip all of those details and only claim here that basically what you're seeing is the ultimate solution, and what it does, it effectively separates the original entire population into a set of 4 mutually exclusive segments such that you have different death rates or different response rates as you go from a segment to a segment. And the job of CART was to identify the optimal subset of splitters to allow for the as precise segmentation as possible in terms of separating one group from the other. And in this case, we have 4 segments. They can all be arranged according to the risk of dying, starting with terminal node A at the 70% risk, followed by terminal node C at 50%, followed by node D at 11%, and followed by node B at 2%. And that's the job of CART. Now, furthermore, CART identified that all you need to know is the person's blood pressure, the person's age, and whether there is a history of irregular heartbeat or not. And only those 3 variables out of the original set of 19 are already sufficient to essentially position any given patient into one of these 4 different risk segments, the different risk profiles. Now, once you have a solution like that, never mind that the great amount of exhaustive search and mathematics was put inside of the building of that solution. Now, once you have it, it's extremely easy to talk about it, to explain it, and to put it into practical use. It is that part of the ease of explanation that sounded so appealing to medical doctors out there, because it technically relates the actual thought process when a diagnosis needs to be set for any given patient. You basically ask a series of questions, you observe certain straightforward things and measurements, and based on the combination of those, the ultimate decision is being proposed. So, and these are the kinds of things that you need to look at, and those are the kinds of things that are making CART an extremely appealing application in terms of the final result, the final model. Now, what you will also find interesting about this solution is that, first of all, it's hierarchical in nature. It does give you segmentation in the end, and it cannot be expressed as a plain old logistic regression equation or some kind of linear equation. So all the variables are allowed to interact with each other, even though interactions might not be explicit here, but they are built within the tree structure itself. And in the end, you're getting both the segmentation solution as well as the solution that takes into account a kind of a variable selection and automatic discovery of the useful patterns and the useful shapes that are present or exist in your original data set. And that's essentially the beauty of CART, the kinds of ideas that Breiman, Friedman, Olshan, and Stone spent and dedicated large chunks of their lives to evolving it, explaining it, and essentially making it available through us as Salford Systems to the wide variety of analysts out there. This part kind of concludes that initial historical and theoretical introduction into CART, and what follows, I will go ahead and demonstrate the actual work of our software on a few typical examples. What you're seeing in front of you is a so-called CART GUI interface. Now, CART itself comes as the non-GUI engine that could be compiled or assembled for the different types of platforms out there. We have different versions of Cart running on Unix platforms, Linux, Mac OS, more exotic platforms. So as long as we have access to the compiler that exists or developed for those platforms, we will be able to compile the non-GUI Cart engine for you. Now for the GUI platform only, we also have that extra development effort to produce the GUI interface that would help you to work with the Cart engine in a seamless way. So in other words, on the GUI interface, you don't have to worry about memorizing different commands or mastering all kinds of command line use, etc. So what I will do here, I will use this GUI interface to build a simple classification model. And what we're going to start with is building a model that attempts to predict spam emails. You start by opening a data file. And when you open the data file, well, Cart itself is an analytics engine. So it is assumed that your data already exists as a kind of flat table in a flat shape. And you have columns for variables, you have rows for observations. And we're also assuming that you already know what your target variable is. And then for the case of classification runs, the target variable is required to be a categorical variable with at least 2 distinct levels. Now what I have here is the data set called spam base. It's a CSV ASCII delimited data set, but Cart itself also supports a direct access to a variety of different statistical formats. In fact, every major statistical format that you will find out there is directly supported by Cart. So you can open different data sets. You can also save the results of your scoring into those alternative data formats. So you are not kind of stuck with only the proprietary format that we might have supported otherwise. But in this case, I'll use the simplest and the most widely used format, which is the ASCII delimited CSV dataset. When you open the dataset, a little information window pops up that explains the number of records, the number of variables, and also lists variables by names, as well as gives you alternative statistical definitions and information. Now you can do from this screen quite a few things. For instance, you can move on to the stats window and gather all of the individual univariate statistics on either all of the variables or a subset of variables. You could view the data the way it has the physical kind of natural feel, or you could go to scoring mode if this is what you are currently interested in, but scoring naturally assumes that you already have certain models in stock that you built at some earlier stage before. But most of your work will be spent in the modeling window. So I will skip all of the remaining windows and you will be able to figure out how to work with those on your own. But the model window brings you proper to the core of the Cart engine. And in the model window that we call model setup is essentially your way to control what is happening inside of Cart and what are the different control parameters that you are going to set for the engine itself. So I'll start with classification run, and when I pick my target variable, it's called target, and I already know that it has 2 levels, spam versus no spam. Now all of the remaining variables are to be considered as potential predictors. Now what we have here in this data set is a very simple-minded and straightforward technique, generally known as a bag of words. So we have a collection of 4,000 plus emails, and each email has been described by the percent presence of some of the key most influential words. So each word from this list is presented by its fraction or percent in the data set in the email body to which the given record is actually referring to. So it's mostly word presence as well as some of the text summary statistics like capital run length average, or what is the average length of blocks of text all written in capital letters. Likewise, what's the longest such sequence and what's the total length of all such sequences. So something along those lines. It's a publicly available data set, has mostly historical reasons, and naturally spammers have evolved way beyond the simplicity of this data, but it does have an interesting and illustrative kind of a service to us. So I work in classification mode. The next important thing that you always have to take care of is to address the issue of partitioning your data set into train and test components. Now, with large data sets, you can usually afford direct partitioning into certain percentage of the data as a learn sample and a certain percentage of the data as the test sample. In those cases, when you have a very small data set, you may actually consider an alternative to that partitioning, generally known as cross-validation. Well, either way you proceed, the key here is the testing tab that allows you to choose among a number of different partitioning strategies, including one strategy that uses all of the data set for learn sample and essentially disables or ignores potential validation side of things. Now, the reason why we want to partition into learn and test is because we want to exercise the full power of the CART engine itself in order to build a series of models of a progressively better and better predictive power on the learn sample. But in doing so, there is always a danger that the new models, that the more elaborate the model gets, the more tighter it describes the actual learn sample and becomes less useful in the most general sense. So in order to prevent that from happening, we normally allocate an independent piece of data that is set aside and not directly participating in the model building process. And only at the very end, that independent test sample is used to judge the model performance for models of a different complexity and a different degree of localization. And the model that gives us the optimal performance on the test sample is suggested as the optimal model overall. In our case, I will go ahead and pick a fraction of the data set available for testing. So I will ask CART to randomly allocate 50% of the original data for testing purposes, and the remaining 50% used to build a sequence of models and use it as the learn sample. Now, the reason I'm using 50-50 is because I want to be able to kind of illustrate the difference between learn and test set performance using counts themselves. In normal practical situations, some people suggested that you will be better off if you use roughly 2/3 for the learn data and only 1/3 for the test data. But alternative configurations are also possible, and it's not easy to claim which way is better, one or the other. Now, in this case, CART kind of takes control over the random partitioning. If you are interested in more specific kind of types of partitioning, you are welcome to try more flexible options, like when the test sample is supplied explicitly as a different data set, or when you supply a variable that indicates whether a record belongs to the learn sample or to the test sample. And those are all kind of flexible options available here, including cross-validation. And there's other things that are basically not worth much of the discussion here, but for instance, sometimes it does make sense to limit certain nodes and to set the limiting size for all of the terminal segments. And that can be achieved in the advanced setting, in which case I've essentially required cart to keep at least 10 or more emails within each of the terminal segments to prevent the proliferation of very small and uninformative tiny little segments. So that's pretty much all of the initial steps that you need to worry about. Of course, cart itself has many more options and settings, but even without touching those, the initial default settings are usually good enough to cover most of your needs, at least for the initial exploratory runs. So when I hit the Start button, GUI generates the proper cart engine commands. The engine executes those commands, and the results are again being recaptured by the GUI side and being shown for you in the form of a navigator window. Now, the navigator window is basically your kind of guide through the tree structure, and not just one tree, but the entire collection of models that originates as the output of the given modeling run. The navigator has two components. The upper half shows the tree in the most minimalistic schematic outlook, and the bottom part shows the tree sequence indexed by the number of nodes in the tree and the corresponding performance on the test sample that is presented in terms of the relative cost. Again, in our cart training classes, we pay more attention to the actual definition of what the relative cost actually stands for, but in this case, it's just some kind of measure of performance. The relative cost normally varies between 0 and 1. 1.0 means that you have a model that is as useful as basically a random guess, whereas the relative cost of 0 would stay for the best perfect scenario when all of the target classes are purely separated. And don't forget that this is calculated on the test sample, which is basically an already applying model in a broader and a more general context. Now, the tree sequence starts at the leftmost side, and this is where you have only the very first tree split. If you look at the tree details, what the split is doing, it's essentially trying to separate a larger chunk of spam emails marked by class 1 on the right-hand side and a larger proportion of no spam emails on the left-hand side. Another visual way to look at that is if you click at the node information itself, which opens up a window that explains what happens inside of that node. And again, in our training, we usually spend more time discussing what the concept of competitor versus the concept of the surrogate really is, but it has some important, profound implications in terms of missing value handling, etc. But for now, let's just look at the bar charts depicting what happens with individual target classes at the node level as the result of the current split point. And as you can see, the majority of class 0 is going to the left-hand side, whereas the majority of class 1 goes to the right-hand side. And that's the ultimate job of that very first split. Remember, at each point, cart engine is looking really hard trying to identify the best way to use a univariate slice in order to separate one class from another. And in this case, it is that variable called frequency of the exclamation mark character. If that frequency is below 0.009, then we are going left, and we have as the result a much lower percentage of spam. If that frequency is above that threshold, then we have a much higher percentage of spam. And this is the best we can do as far as separating spam from no spam using an information available in a single variable only. Once that step has been accomplished, CART goes on and starts revisiting each of the new subsets, and it searches for the next best way to partition that segment over and over again until the tree is kind of growing to the largest possible size. At this point, the tree can be no longer expanded because either the nodes are becoming too small or CART fails to find useful ways to separate one class from another. Once that has been done, the sequence itself undergoes the so-called process of pruning, which essentially constitutes looking at the large tree, identifying the least important, the least valuable components of that tree, and progressively removing those components, thus reducing the size and the complexity of the tree itself. And that process of pruning gives us the raw material in the form of the sequence of models. Now, all of these trees are nested within each other, and they are serving as a potential candidates to become final models. Once the pruning process is being finished, that sequence of models, each and every model from that sequence is being evaluated on an independent test sample. In my case, it's that 50% randomly allocated by CART before the run commenced. And the performance as far as the relative cost goes on the test sample is presented as this curve, and the tree configuration that has the minimum relative cost on the test sample is highlighted by the green light, and it's shown as the optimal tree. Now, it's quite natural when you look at that tree, you either accept the tree as is, or you evaluate it in somewhat different terms. For example, you could look at the area under ROC curve on the test sample and observe what happens to that measure on different models. Like in this case, going towards larger side actually improves test ROC a little bit. Or you could use your pragmatic considerations and look at smaller trees in order to understand a kind of rougher and bigger picture segmentation without being bogged down into all kinds of technical and non-essential details. I mean, one could argue that this relative cost is already good enough, and it is achieved by running a much simpler tree that will be a lot easier to explain or understand. Now, suppose I'm interested in this tree, and I mean, what are the alternative ways to look at that tree? Well, first of all, note that some of these nodes are marked in red colors, and these are the nodes that have large concentration of +1s, and the +1s mark spam. And you also have blue nodes that have larger concentrations of zeros, which are no spam. Now, you can connect or bind red versus blue color coding to different target classes based upon this dialog up above. Now, if I switch to 0, it changes to 0. If I switch to 1, the color coding kind of reverses itself. Now, once you have that tree, it is also important to realize that some nodes are small, whereas other nodes could be large. So even though all nodes look of identical size here, in reality, some nodes have a large number of cases, whereas others have a relatively small number of cases. We have a mode inside of the GUI engine, which is available by clicking on this button twice. that shows relative node sizes in cases. And as you can see from this distribution here, we have one major node on the left that's marked in the blue color, and that's the node that has a 92.2% of no spam emails. We also have another node here, node 6, which actually has 90.1% of spam. And if you go inside of that node, you can actually confirm that that behavior of being predominantly spam node holds between learn and test samples. And once you switch the rules immediately tell you the conditions that lead to that abnormally high presence or concentration of spam emails. Now, for example, it needs to have high frequency of exclamation mark, low frequency of word HP, the presence of all these all capital run sequences, as well as a low frequency of the word edu. If all of these four conditions are met, then we have an increased and largely increased odds of getting a spam email associated with that document. On the other hand, the previous node that was largely no spam, again, you could confirm the rules and the performance on the learn versus test samples. And the rules here are basically an alternative set, not overlapping with the previous set jointly, and it basically tells us the rules and conditions that lead to a node being predominantly no spam node. And those two cover a large chunk of the population. The remaining nodes that you see are kind of additional small scale slicing here and there that essentially allow the tree itself to identify additional segments that are pure in one or the other target class. So that's one way to look at things. Another way to look at the tree itself is by looking at the splitters information, which gives you kind of next level of detailization, where you not only see the tree topology, but you can also see the names of variables that are directly participating in the splitting process at each of the internal nodes. Or you could also request a tree details display, which shows the definitions inside of those nodes and the general in a more conventional look. So when you look at the individual nodes, you actually get to see what are the percentages of individual classes, what are the splitting rules, what is the overall node count, etc. And under view node detail, you actually have a very fine control over various pieces of information that can be displayed at both internal node level and the terminal node level. Everything can be saved as a default, and you're welcome to try it in order to configure the actual final look and feel of the display itself. There's another useful thing here is that, as an example, if I look at the largest possible tree, when I look at the tree details, because of the limitations of the computer screen, it becomes sort of almost impossible to understand the actual tree structure, which is where the navigator file approach kind of makes it more intuitive. But what you can also do, you can go ahead and turn on the print feature, and the print component already shows the approximate allocation, basically how the tree will occur in print if you send it to the printer now. Now you can also manipulate page setup to change, for instance, things to landscape form, maybe impose a little bit of scaling here and there, and in any case, essentially accommodate that large and complicated tree on multiple sheets of paper so that it can be later assembled and perhaps published on the wall or on the floor or anywhere, in case you're one of those people who really want to see the tree in its entire span and not by an artificial way of a navigator window. So that sort of covers all of the original important pieces of the cart model setup and the cart display. Now, what you can also do, in addition to working with the tree itself at the node and rules level, you can also request overall summary reports. And the summary reports, you get to see things like learn versus test performance in terms of gains, lift, area under ROC curve, and the ROC curve itself. You can even superimpose learn and test performances on top of each other. You can look at the terminal nodes and how they are whether they are stable or not stable based on the learn versus test set performance. Now, some of these features are later discussed in our comments and introduction to the CART Pro EX features, which is one of the most advanced Pro versions of CART. Now, at this stage, it's not that important. I will just mention that these summary displays are quite useful in general understanding of what is going on with your model and how it looks and feels. Same goes for variable importance, one of the most influential displays. Some people run CART just to get to see this variable importance and use it as the means to subset variables according to their contribution to the model. Now, I have to be a bit careful with this display because it basically shows the contribution of variables as presented in the current tree. So if you look at the very large tree that is unjustifiably large, then you will see more variables as important. And likewise, if you go all the way back to the tree that has only a single split, you will see only a few variables as being important. It is usually a good practice to look at the variable importance display associated with the optimal tree, or at least trees that are somewhere in the vicinity of the optimal tree based upon one or another evaluation criterion. You also get to see things like prediction success, again, both in the learn and the test sample. Now, needless to say that the learn sample prediction success is somewhat overly optimistic because, after all, it is the learn sample that has been used to build the model itself. On the test sample, we get a fair estimate of the performance, assuming that the test sample has been large enough or indeed randomly drawn from the learn sample, which is what happens in my case. And according to that performance evaluation, it looks like we are 92+% accurate in correctly capturing no spam emails and about 88-89% accurate in capturing correctly the spam group. Now, if you're interested in changing the balance, and some people call it false positive, false negative rates, things like that, again, as part of our advanced CART setting, as well as part of our CART classes, we talk about the important concepts of priors and costs, and those are immediate and the most influential factors that would allow you to take the existing CART model and rebuild it and reshape it into an alternative model that has a better or alternative capabilities of balancing out false positive and false negative rates, or the different pieces of the performance and accuracy that you may find here. Another useful feature of CART, for instance, if I look at the summary reports and the ROC information associated with this run versus ROC information from a very much smaller tree, what I could do in this case is basically look at my performance here and see how it changes as I go between learn and test samples. Or I could build another model, let's say, with maybe an alternative distribution of priors, and now request another alternative display, and now attempt to look at both ROC curves in some kind of, well, let me put it this way, simultaneously, so that they are superimposed on top of each other. I mean, that's a very useful, practical feature of CART that has nothing to do with the engine itself, but it does illustrate what happens when I change certain important control parameters of CART, like in this case when I touch the prior probability control and change it from one predetermined setting to another predetermined setting. And the natural result here is that I'm kind of balancing out my ROC curves. I'm either making them steeper initially or more gradual at the initial segment, but at the same time there's the opposite trade-off at the different the alternative percentages and alternative parts and areas of the consideration here. So in any case, those are some of the real interesting and important pieces that I would urge you to look at. And for the most part, it kind of illustrates how one works with CART, at least at these initial exploratory levels when you're only working and looking at one model at a time. CART also has an important regression tree component that I usually talk about as part of our training classes, and you're welcome to try it on your own as well. And we also have a very important additional machinery inside of CART that essentially produces a series of automated runs according to a predetermined modeling strategy to explore different and the various aspects of the modeling process. I mean, we call those batteries, and those are one of the biggest add-ons to the most latest professional version of the CART engine. So we have a separate presentation dedicated to just expounding on some of those ideas and some of those new features and considerations. But other than that, hopefully, this is a little bit of a general overview, enough to get you started and enough to get you going with all of the key initial issues and the details of the interface. The machinery itself is quite amazing. Once you get used to it, it's sort of hard to switch to something else. I mean, once you learn and understand the true powers of CART and its capability to capture underlying structure and signal, and especially in its ability to work with missing values, it essentially expands your horizons to a new level. And it's very hard to do something else once you get in love with CART. The way that happened, I mean, this is something that happened to me many years ago. Of course, I evolved my understanding past CART into more exotic products like Mars and TreeNet. But all in all, to this day, I would say CART is one of my favorite products, and there are certain areas in the applications where you can hardly use anything else, and CART will still remain one of its biggest and the most appealing faces. Okay, that was it. Hopefully you'll come back either for our training classes or additional presentations expounding on some of the basic features of CART. But other than that, I wish you all the best, and good luck with your endeavors.